Welcome everyone to another lesson on Khadija Academy. Before we start this lesson, hit the subscribe button, the notification bell, and the like button for the YouTube algorithm. Now let's go and start our lesson. Hi and welcome everyone to our course for control systems. In this video, we are gonna discuss the fractional order PID controllers. We will discuss the difference between the conventional PID and the fractional order PID with the mathematical derivation. So we'll start with the PID controller, which is a proportional, integral, and derivative. The PID controller in industry is one of the most commonly used controllers. Now, it works by combining three actions: the proportional, integral, and derivative. So we have these components. Proportional reacts to the current error, integral reacts to the accumulated error, and derivative predicts the future. Now, what does this even mean, or how is this even mathematically possible? So if you look at this one, this is the transfer function in the S domain for the PID controller. This is the transfer function of PID controller. So you'll see it consisting of three components: proportional, integral, and derivative. So how will this even do these three functions? So in reality, when we say the control signal, the output will be equal to the error, the current error, multiplied by the transfer function of our PID controller. So this will give us the control signal. So this will be KB multiplied by E of S plus KI 1 over S multiplied by E of S plus KD multiplied by S multiplied by E of S. So let's look at this. This one reacts to the current error. So based on the current value, the input value to the PID controller, it reacts. That's why it's called the present control action. It acts only to the present value of error. It doesn't care about the past or even the future. However, for this one, this is an integrator. This looks at the accumulated error. For example, it looks like this. So if we have the error like this with time, like until this instant here, so this is the error with respect to time. So what happens is that this controller takes the integration, 1 over S means integration of error. So it means until now, it takes the integration of all of this, of our function like this, until this moment. That's why it acts for all of the past values. So it takes the history of our values. So that's why it called reacts to the accumulated error over time. So this is past, this one for the present. Now what about the last one, which is derivative, D? So KD multiplied by S multiplied by error, S meaning the derivative, D over dt of our error in the time domain. So simply the rate of a change of error. So what does this even mean? It means it takes the derivative at this instant, at this time here that we are doing. So if you look at the derivative, it looks like this: the slope of the line at this instant. So based on this slope of the line, it predicts that the error will go up. So based on the slope, it predicts that it's going up. So based on this, it predicts the future. That's why this one is related to the future, because the derivative or a change of error like this. So the error at n is like this. So by taking the derivative at this time, I say, hey, due to this derivative, I predict that the signal is going up or the error is going up. That's why this one acts for the future. It prepares for the future. That's why in the end, reduce the error, current value, past mistakes, which is the integrator, and prepare for the future for the derivative. Now, what about the fractional order PID? So we have a branch in mathematics called the fractional calculus. So fractional calculus relates to not the integrator itself, not the integration of the function or the derivative of the function, but let's say that instead of getting the first derivative or first integrator, what does this even mean if I say, hey, what about let's get half of the derivative, half of the integrator, or half of the derivative? What does this even mean? So we have a function like this one. Let's say the function is maybe a straight line like this, x. So its first derivative will be a constant of 1, like this. This one is first derivative, d over dt of x. Now, if we take its own integration, it will be a x squared over 2, like this, x squared over 2. This one representing integration or first integration of x. So we have derivative and we have integration. Now, between this, we can find the fractional integral. What I mean by this, let's say half of the derivative or quarter of the integrator, half of the integrator, quarter of the integrator. Between these two, we can find like this, half of the derivative, and so on. This has some applications in real life. Now, why do we even do this inside our control system? Now, if you look at here, this acts to the integration of error. This one acts to the derivative of error. Now, let's say I don't want it to be much aggressive. I want it to be less aggressive. What I mean by this, I don't want a complete pure integration. I just want a little bit of integration, a less aggressive. And instead of very sharp derivative, I want it to be a little bit aggressive. How can we do this? So in a normal PID, we have integral and derivative, these two coefficients, s to the power 1, s to the power 1. Now in the fractional order PID, we can control this integer here. Instead of 1, we can make it a real number between 0 and 2. So this give us more degree of freedom. And instead of optimizing 3 gains, KB, KI, KD, we can KB, KI, KD, 3 gains plus the power of S and this power of S, these two powers. So we have 5 parameters that needs to be optimized. In fractional order PID, we call this power lambda and we call this one mu, between 0 and 2. Don't worry, I'm gonna explain how can we get the mathematical derivation of the integration, fractional integration and fractional derivative, as we will see in the next slides. So what is exactly fractional calculus? So we have this equation here. In basic calculus, we have first integration, which representing integration of the function, which is area under the curve. And the first derivative is the slope or rate of a change of the function. Now, what does this mean when we have half integral or half derivative? That is what fractional calculus does. It takes in between these values. So for example, we have a function here, f of x equal to x squared over 2. Now, d over dx to the power alpha, we would like to get its derivative. So let's say if d over dx alpha equal to 1, which means we would like the first derivative of the function. Its derivative will be simply x. So this is our function, alpha equal to 0, no integration, no derivative. This one is x squared over 2. When alpha equal to 1, it will become x, which is like this. Like this. Now, what about the alpha minus 1? Alpha equal to negative 1. So instead of d over dx minus 1 of x squared over 2. This is exactly means integration of the function x squared over 2. When instead of having a positive integer, negative integer means we will reverse from derivative to integration. So integration of this function will be x cubed divided by 6. So it will be this function which you will see right here, x cubed over 6. Now what you can see that if we say I want half of the derivative or half of the integration, it will be, this one will be in between integration, this one will be in between of the derivative, between zero derivative and full integer derivative. You will see these lines, each of these lines gives us different response. So instead of having a strict response like this for the derivative, we can select what we would like this. And similarly for integration, this also gives us different degree of freedoms or extra degrees of freedom to give us a more stable response or a more smooth response of our system. Here is another example. You can see we have the function this one yx squared, which is this one, and when we apply this derivative, as you can see here, you will see there are different values in between. So this is the first derivative and this one second derivative. Between them there are many lines representing the fractional orders. Okay, so the question is, how can you get the fractional integral and the fractional derivative? So we need a derivation or a mathematical way to find this. So we have integration and we have derivative. How can I convert this into half derivative? So the principle at which the mathematicians found the half fraction or fractional order and fractional order integral and fractional order derivative is by using the Cauchy principle or Cauchy's repeated integral. So what does this mean? So let's look at this formula here. It says that if you would like to integrate a function n times, so I refers to integration of a function f of x n times, it will be 1 over n minus 1 factorial of n minus 1 integration from a to x minus tau n minus 1 f of tau d tau. Okay, so tau here is called a dummy variable, just a variable in order to do this integration. So simply we took f of x and we made it f of t of tau d tau. I'm gonna show you an example right now on how to apply this formula to understand it. So this is for n becoming integer, let's say 1, 2, 3, 4 and so on. So this is for doing the integration several times. Okay, so let me show you how to do this. So let's say we have a function f of x equal to x, very simple function, and we would like to integrate this function 2 times. Integration of it 2 times. Let's do it by conventional way. So I'm gonna integrate it once. Integration of x dx will be simply x squared over 2. Now let's integrate it another time. X squared over 2 dx equal to x cubed divided by 6. So this is the integration of this function 2 times. Great. Now how can I do this quickly using Cauchy's formula? So we will have 1 over n will become 2, since we would like to integrate it 2 times, minus 1 factorial. Integration from a until x. Okay, this is a definite integration, as you can see. Don't worry, we were gonna see what will happen in the end. So we will have x minus, since we need x in the end, minus tau. This is a dummy variable which we are gonna use n minus 1. N here is 2, so 2 minus 1 gives us 1. And we have f of tau. This is a function, same exact function, but instead of f of x, we will gonna make it f of tau. So it will be equal to tau, like this, d tau. So 1 over 2 minus 1 is 1 factorial, which is just 1. So this one is 1, multiplied by a 2x of our function x multiplied by tau, x tau minus tau square d tau. Remember, we are doing this integration of Cauchy with respect to tau. So we will have integration of tau here will be tau square over 2 minus tau cube over 3 between a to x. So this will become, first we will substitute with x, so it will become x multiplied by x square divided by 2, h tau replaced by x minus x cube divided by 3. Okay, minus, this is the initial condition which we didn't have here, so we can neglect this for now. So we will have x, so this will be equal to x cube divided by 2 minus x cube over 3. By doing this subtraction, you will get x cube over 6. This is the output of our integration, exactly similar to doing integration 2 times. So this is Cauchy's formula. It doesn't have anything to do with fractional derivative or integrations. This is a principle for doing integration several times. So the scientists or the mathematicians they thought about how can I use this formula for fractional order. So they said, hey, what if I say instead of integrating it by 1 to third, what if I substitute it with half, for example? Let's use this formula to get half integration. So this is what they do. So when they are substituted like this, half of integration, it will be 1 over 0.5 minus 1 factorial integration a to x, x minus tau, n minus 1, which is 0.5 minus 1, f of tau d tau. This integration is nothing hard with this integration. However, for this one, we have factorial of negative 0.5. So they thought, hey, this is factorial negative 0.5. What does this even mean, or how can I get this? Because we know factorial is for, let's say we have 3 factorial, means 3 multiplied by 2 multiplied by 1. 2 factorial is simply 2 multiplied by 1, and so on. So what does negative 0.5 factorial even mean? So what they did is that they used another formula for this in order to get this value. How? By using the gamma function. The gamma function can take factorial, negative factorial into another form that can be computed. So let's see this. So the factorial replaced by gamma function, gamma of n is simply n minus 1 factorial. So let's say if we would like 0.5 minus 1 factorial, this will be equal to gamma of 0.5, which can be computed. So we replace this by our gamma function. This is our gamma function if you don't know about this, and this is the mathematical equation or integration at which we obtained the gamma function. Okay, so here we replaced 1 over gamma of n, x, a to x, and so on. Now when we talk about integration or fractional order integration, if you remember, we said we have ki over s to the power lambda plus kd multiplied by s to the power mu, right? So since I'm talking about 1 over s to the power lambda or fractional integration, I'm gonna make this, instead of n, we will make it lambda, like this, to make it the formal notation. So fractional order integration of power lambda will be 1 over gamma lambda and n becoming lambda, as you can see this. This is what we call the Riemann-Liouville fractional integral. These are two mathematicians that use the Cauchy's principle in order to Cauchy's repeated integral in order to find the fractional integral. So this is a formula by Riemann-Liouville. Okay. Okay, what if lambda equal to 1? So for example, this function should also lead to the same integral, right? So if I say lambda equal to 1, it means I'm doing a full integration of power 1. So let's do this. So I1 f of x equal to 1 over gamma 1 integration from a to x minus tau. Here it will be to the power 0 since lambda equal to 1 f of tau d tau. So this will be equal to 1 over gamma of 1 will be 1 multiplied by integration of a to x of f of tau d tau. So it is simply the same exact thing. Why? Because this is a dummy function. So if I say f of x dx, it is the same as integrating f of x. So nothing changed. It is the same exact formula as you can see here. So saying f of tau d tau is exactly the same as f of x dx or f of y dy, because we just changed the variable from x to tau. Okay, so this is the integration form. So how can we get the derivative? Okay, so the principle at which they thought about this is as follows. So this is the integration, right? This is a fractional integral. So how can I get fractional derivative? The philosophy is pretty simple. Okay, so let's say I would like to get d by dt, let's make it 0.2. So I would like to get the 0.2 fractional derivative of a function f of x. So let's think about this. So what if I did like this? So we know that derivative, full derivative, and a full integration of a function cancel each other, right? 1 and this is 1, they cancel each other, making us we have f of x. If we did double the integration, double the derivative, multiplied by integration, this will be 2 derivative, 2 times, minus 1 integration, giving us in the end one derivative, which is d over dx f of x. So they say, hey, we want to get a fractional derivative of this. How about we do a fractional integration of, let's say, 0.8 half of x. This one, fraction of integration of lambda equal to 0.8. And then let's take the full derivative, d over dt of what coming out of this. So think about this, we have a fractional integration, so we are integrating by a factor of 0.8, and we are taking a derivative of 1, a full derivative. So if you think about this, you will find that simply 1 minus 0.8 gives us a derivative of 0.2, right? Similar as here, we are subtracting derivative from integration, derivative from integration. So by taking a fractional integral of 0.8 and a full derivative of 1, their net 1 minus 0.8 gives us the net derivative 0.2. And this is the philosophy behind Riemann-Liouville fractional derivative. They say, hey, we take a derivative, okay, a full derivative, n is an integer. And then we say, hey, take a fractional order integration of n minus mu. Mu representing the fractional order of the derivative that we want. So let's see how this even applies. So let's say we wanna get derivative of 0.2, right? Fractional order derivative of 0.2, which corresponds to mu, which is this parameter here. So this will become 0.2. Now what does n exactly? N is the next higher integer than mu. So n greater than mu. So for example, if mu 0.2, the next higher integer is n equal to 1. If mu 1.5, then the next higher integer n will become 2. So n here is the highest next integer. So in our case for 0.2, n will become 1. And n here will become 1. Exact like here, you can see 1 and n minus mu, 1 minus 0.2 gives us 0.8. So this in the end, let's leave this, in the end, you will find that we have an integration of n minus mu, derivative of n. So their net will be derivative minus the integration n minus mu. So this will be n minus n plus mu. So the net will be mu derivative, or a fractional order derivative of mu. Okay, so this is our Riemann-Liouville fractional derivative. And as we said, n is the smallest integer greater than or equal mu. It should be after mu. So by doing this, we have our function here. It will become, instead of lambda, it will be n minus mu. And lambda minus 1, it will be n minus mu minus 1. And the derivative, as you can see here, I integration d derivative, lambda meaning the power of the fractional integral, and the mu power of fractional derivative. Now, not only this, you will find in some notations, it can be a to x, down of the I, or a to x here. What does this mean? It means our limit are from a to x, like this. Great. So this is Riemann-Liouville fractional derivative. Okay, so what we do is apply a fractional integral of n minus mu, then take the nth integral derivative. Now there is another format for this, is Caputo fractional derivative. Okay, what's the difference between this? This is exactly same as what we did right now, but we inverse the order of operation. So what does this mean? So look at here, what we did is that we took first, we have the function f of x, which is here f of tau. As you can see, what we did is that we took fractional integral of order n minus mu, then we took the derivative, right? So their net will give us the fractional derivative. What if we do the inverse? What do you mean by this? What if we take the function first and we took its derivative, dx dn by dx of n. Let's make this one x for now. So we took its derivative first, which is denoted by dash. So this is equal to f of dash of x. And then after doing the derivative, we took the fractional integral. So instead of starting with fractional integral, then derivative, we start with the derivative, then fractional order. In the end, they should lead to the same solution. They should, okay, but this would not happen. So the Caputo reverses the order of operation. Apply the integral derivative first, then a fractional integral. So if you look at the function here, we took its own integral derivative, this one for the function, and then we applied the integration, this one. So you can see they are inversed, as you can see right here. So let's look at this, d to the power mu of fx. Derivative again is simply the first, the function here, f of tau. Remember, after we took its derivative, we just replace hx with tau. The same exact thing. This is a dummy variable for this integration in order in the end to have a function in x. Okay, and then after taking the derivative, we put it here inside, same as here. And then we apply the fractional integral. So we did the derivative first, then fractional integral. Great. So you can see the same exact thing, except that we start with derivative, then fractional integral order. Now the question is, for our control systems, which one is used for continuous S domain or continuous time domain or continuous control? The one which we use is the Caputo fractional derivative. Why Caputo fractional derivative? Because it is more close to the natural behavior of derivative. Let me explain what happens exactly. So let's say we have an error as a function of time equal to 5. So our error is like this. A step function at a certain time, let's say t equal to 1, like this. Error as function of time, like this. So e as a function of time equal to 5, our step function at this instant. So we need to add here a delta, but forget about this now. Let's just say 5 as a constant here. Let's see what will happen if you apply these two. So let's look at this. So the first, for the Caputo, what does it do? It simply take the derivative. Okay, take the derivative first. So we have our function f of x is equal to 5. So its own derivative will be equal to 0 because we are taking the derivative of a constant. So it will become 0. So when we substitute it here, 0 in this integration, by integrating 0, you will have finally 0. And if you look, the function error is constant. There is no change in the function. So by logic, the normal derivative gives us 0. So it gives us the same exact behavior for a constant function. Great. So it acts similar to the normal derivative for a constant. And this is what I want. I don't want it to act when the function is constant, because it only acts for rate of a change of a function. Now what about the Riemann-Liouville fractional derivative? So we will integrate the function first. We will take its fractional derivative. So we have 5, and when we integrate it, we will have, let's say, for example, just for simplicity, 5 x to the power half over 0.5, just as an example, okay? Plus certain constant which is dependent on the initial condition at time equal to 1, for example, okay? We are integrating from here, let's say we are integrating from 0 until this instant, for example, okay? For this fractional order, so we will have value of the function 5x to the power half at the current instant, okay, plus a certain constant representing the initial condition. Now if we take its own derivative, okay, this one may go, but this function still exists. It is half 5x to the power blah blah blah. So we will have a function here. It is not 0 like Caputo, because this one is, since it is a fractional derivative, it has part of it which acts like an integrator. It looks at a part of the history. That's why fractional derivative of Riemann-Liouville has a part of the initial condition. It affects my current state. Unlike the fractional derivative of Caputo, which acts only on the current value, which is 5, which is constant, which naturally becomes 0 like any other derivative. So I hope you now understand the mathematical derivation of fractional derivative of Riemann-Liouville and fractional derivative of Caputo and the fractional integration which we discussed in this video.